So, everyone's here. I'll get started with the announcements. So, the first homework assignment, the getting started with WebAssign assignment, is due tonight. It is due. It will be due at 11 p.m. tonight because I would like to set it. For some reason, Cengage has decided that we are in Eastern Standard Time, even though we are not. So the due date is at 11 p.m. Well, I mean, it's actually 10:59, but basically 11 p.m. This is really easy, so you should be able to do it, no problem. Chapter 1.1 homework. It's actual homework that will take actual work. That's due on Friday the 5th. As usual, if you need an extension, you can request an automatic extension or a manual extension on any assignment. Chapter 1.2 homework will be due on Wednesday the 10th. So that's next week, Wednesday. 1.2 is much shorter than 1.1. Most of chapter 1 is in 1.1. The chapter 1 quiz will be on Monday in the SCIE session at 1 o'clock next week. So next week on Monday at 1 in your SCIE session, you're having your quiz on chapter 1. And lastly, the significant figures worksheet is due on Wednesday the 10th. Anyone who doesn't have this, I can give you a copy. You said you had it. So fill that out and turn it in on Wednesday in class. None of this information is new. So do keep track. We'll be finishing up chapter 1 today. So we were discussing scientific notation. And so in scientific notation, we have a number expressed as the product of two numbers, where we have some small number between 1 and 10, like, I don't know, 2.75 times the power of 10. 2.7 times 10 to the, I don't know, 4. So 2.75 times 10 to the 4. This is a more compact way of writing 27500. These are the same number. And to convert, you move the decimal point. So here you go 1, 2, 3, 4 steps to the left. Every time you move the decimal point to the left, you add 1 to the exponent. Every time you move the decimal point to the right, you subtract 1. So big numbers end up with a positive power. Little numbers, smaller than 1, end up with a negative power. The metric system. We've been talking about the metric system. The metric system uses the MKS acronym from the standard units of length, mass, and time. These are the meter, the kilogram, and the second. It is a decimal base 10 system. This is more convenient than the British system. So every conversion is pretty much every conversion is multiplying or dividing by a power of 10. So it just really involves moving the decimal point. And everything is expressed with a standard set of prefixes, which modify the base unit. This is administered by the Bureau International des Poids et Mesures in Paris, and it's called the SI system for the International System of Units. And there are 7 base units in it. So the 7 base units for the metric system are the meter for length, the kilogram for mass, the second for time, the ampere for electrical current, the Kelvin for temperature, the mole for amount of substance, and the candela for luminous intensity. Of these, we're going to use the first three primarily. We'll use some of the Kelvin when we talk about temperature. And I might mention the ampere. The ampere gets used. The mole is used in chemistry classes. This is not one of those. And the candela, I don't think there's a single class in this school that uses the candela. Oh. I've never used the candela. I have a PhD. Let's put it that way. It's used in very specific situations. The metric system has a set of prefixes. Each prefix corresponds to a power of 10. A reminder, if you're having trouble remembering these prefixes, do expect you to know them, but you are allowed to write them on your sheet of notes you get for every quiz or test. So for all tests and quizzes in this class, you get one sheet of notes to use as a formula sheet. So if you're having trouble remembering the metric prefixes, put the table of the metric prefixes on your formula sheet. Then you'll be able to remember them. So each prefix corresponds to a power of 10. And if you have that prefix in front of a base unit, it's the same as multiplying that unit by that power of 10. So a milligram is 10 to the minus 3 times a gram. It's 1,000th of a gram. A kilogram is 10 to the 3, 1,000 times a gram. It's 1,000 grams. And so from the smallest, pico is 10 to the minus 12, nano is 10 to the minus 9, micro is 10 to the minus 6, that's million. Milli is 10 to the minus 3, that's 1,000. Centi is 10 to the minus 2. Deci is 10 to the minus 1. Kilo is 10 to the 3. Mega is 10 to the 6. Giga is 10 to the 9. You probably know what the one that comes after giga is. It's tera followed by penta. Because those get used in computing. So significant figures are what we're going to discuss primarily today. So significant figures are a way of expressing the precision of a measurement and how precisely you know something from a measured number. So any mathematical operation like multiplication, addition, division, or subtraction cannot give you more significant figures than you start with. That's almost true. So that's generally true. There are some exceptions. I'll point them out. If you do this on tests or quizzes, you'll be fine in this class. We'll go over the stricter rules, but I will always accept you round to the number of significant figures that you started with. So for example, 6.8 has 2 significant figures and 1.67 has 3 significant figures. So if you multiply the two together, 6.8 times 1.67, what you'll get on your calculator is 11.356. But you can't have more significant, but that would have 5 significant figures. And you can't have more significant figures than you started with. So the worst of your inputs was 6.8 with 2. So we have to round this to 2 significant figures. We would round it to 11. So that, strictly speaking, is what you have to do always for multiplication and division. Division is a real issue because when you divide something, it often gives you lots of digits. Because your calculator does nothing about significant figures, it just gives you as many digits as it can calculate. So if you have something like 6.8 divided by 1.67, that equals 4. On your calculator, it'll say 4.0718563. You would round that up to 4.1. You have 2 significant figures, counting from the front, 1, 2, and then the next digit is a 7, so you'd round up to 4.1. So the general rule is that you only report as many significant figures in the result as there are in the least value. The strict rule is that you use number of significant figures for multiplication and division and number of decimal places for addition and subtraction. That's the strict rule. Usually that turns out the same. So here, for example, 6.8 divided by 1.67. This you can round off 4.0718563 to 4.1. And here we have 5.678 plus 11.11. Both of these have 4 significant figures, so we would round it up from 16.797 to 16.80. That's if you use significant figures. However, because this is addition, strictly speaking, you should use decimal places. But 11.11 also has the least decimal places, and you would also round to 16.80. So generally, both ways will give you the same answer. But strictly speaking, addition should be done with decimal places and not significant figures. And this is why doing something like averaging can actually give you more significant figures than you started with. That will come up in a lab we have later. But on tests, I'll accept if there is a difference in the number of significant figures or decimal places. If there's a difference in the answer, depending on whether you use significant figures or the decimal places, I'll accept both. So you're always safe using just round to the fewest number of significant figures from your input. And if there is a difference, I will accept both. In general, on any thing, you need to write answers to the right number of significant figures. And if you don't, there will be a penalty. If it's a question specifically about significant figures, that penalty is going to be a lot bigger. Okay. But in general, it's not a huge penalty. So how do you know how many significant figures a number has when you're reading it in a problem? So and there's a nice version of these rules on the significant figures worksheet you have that I handed out. All non-zero digits in a number are significant. So 23.4 and 234 both have 3 significant figures. Everything in there is not a 0, they're all significant. Any 0 that's in between non-zero digits, captive zeros in the middle, are also significant. So 20.05 has 4 significant figures because these zeros are in between non-zero digits. And 407 has 3. Now, any 0 on the front, leading zeros, to the left of the first non-zero digit, those are never significant. Because their only purpose is to tell you where the decimal point is. Because I could write the same thing here. I could write the, just as an example, you could write 0.0075, or you could write 0.0075, 0.0075, 0.0075. You can put as many zeros on the front as you want. But the whole purpose of these zeros is to tell you where this decimal point is in relation to the digits. We have to fill in that empty space. Because if we left those out, we'd have a problem. It'd be a different number. So leading zeros are never significant. So 0.000035 has only 2 significant figures. Now, trailing zeros vary whether they're significant. There's two cases. If there is a decimal point, they're significant. If there's not a decimal point, they're probably not significant. It depends on context technically, but so here 45.0 would have 3 significant figures because there's a decimal point, and 4500 probably only has 2 significant figures. So if I wanted to write 4500 with 4 significant figures, what I could do is I could write 4500 and then just add a decimal point to the end. So I will do that on tests sometimes when I want to use a nice round number for a problem, but I want it to have a certain number of significant figures. So if I wanted to, say that something traveled 100 meters, but I wanted you to do the problem to 3 significant figures, I would write 100 point and just point. So you might see something like this on the test. And that's telling you that that's 100 meters, but it's 100 meters to 3 significant figures. If you want to always be safe and make sure all the numbers you write are significant, if you write something in scientific notation, every digit you write is significant. So here 2.75 times 10 to the 4 all has 3 significant figures. All 3 of those are significant. So these are the rules for significant figures. Any questions about that? Now, there's a couple exceptions. Well, there's one big exception, exact numbers. If I have 5 cupcakes, where that's like an exact count, that is an exact number. I know that number perfectly. Or, let's say I want to, or I'm trying to figure out the average weight of these ball bearings, and I grabbed 10 of them. So I have 10 ball bearings here in my hand. There are exactly 10 ball bearings. There are no fractional ball bearings or anything like that. So in that case, I can assume that the number 10 for the 10 ball bearings there has an unlimited number of significant figures. This also applies to numbers in equations. So if your equation has like a 1/2 in it or a 2, that can be assumed to have an unlimited number of significant figures. So like circumference of a circle is 2 pi times the radius. That 2 is an exact value. And so in theory it's pi, but that has infinite digits. So and in the process of determining the number of significant figures, you've got to round off your answer. So when you round something off, you need to look at the next digit along. So here, if I'm rounding this number off to 3 significant figures, 1, 2, 3. In general, if you're counting significant figures for rounding, you count from the first non-zero digit. So I got 1, 2, 3, and then I look at my next digit. So here I've drawn a vertical line for where I'm cutting this off. And I need to look at my next digit to see what I'm trying to figure out is that this number, I have it 26.1. So this value is going to be somewhere between 26.1 and 26.2. And I want to round it to the one it's closer to. So if that digit is less than 5, so over here, this is, 26.142. That is closer to 26.1. So it'll go to 26.1. But if it was higher, if it was 26.170, so that'd be about here, it would go up to 26.2 because that's closer to 26.2 than to 26.1. And so the division is when the next digit is 5, because that's the middle. So if the next digit is less than 5, we leave the preceding digit unchanged. If the first digit to be dropped is 5 or greater, like here, so we have 10.0 followed by a 6. Well, that's 5 or greater. We go up to 10.1. So here are some examples. The one weird exception is here with 0.0097. So 0.0097, I'll write this out on the board. I want to round this to 2 significant figures. Well, here's my first non-zero digit. 1, 2. Okay, that's where I'm going to draw my line. So I'm going to cut it off. My next digit is a 7. 7 is greater than 5, so I will need to round up. So 9 plus 1, that's 10. And we carry a 1. 9 plus 1, that's 10. Carry a 1. So I got 1.000. But there's a problem. 1.000, that has 3 significant figures. Well, actually, what I need is 0.10. That particular situation where you end up with more significant figures will only happen when you have a string of that. So this would round to 0.10. And then here we have 5.0 times 356, which gives us 1780. But 5.0 only has 2 significant figures, so it'll get rounded off to 1800, up to 1800. So basically, you look at your inputs, count your number of significant figures, and choose the lowest one of any of your inputs, and that's what you're going to round your answer. When you make a measurement, with a ruler, the strict rule is that you can read through and then you can estimate another digit in between. I didn't have you do that today in the lab. I'll tell you how precisely I want you to make measurements in lab, but this is an example of how you should, in theory, be measuring. So here, this is a millimeter ruler. If you're here in between 54 and 55, you can estimate that this is about 54.5. So strictly speaking, 54 would be indicating less precision than you're actually measuring, and 54.6667 would be indicating way more precision than you're actually measuring. And so this would have 3 significant figures as a measurement. So in numbers with a decimal point, leading zeros are never significant. Zeros between non-zero numbers are always significant. That's always true, these two. And with a decimal point, trailing zeros are always significant. Without a decimal point, trailing zeros are not significant. And in all numbers, zeros which appear between non-zero digits are always significant. Generally, you don't have leading zeros in a number without a decimal point, which is why they only put it in the with a decimal point section. But that is always true. They're never significant. So for example, 3400 has 1, 2 significant figures and 2 non-significant digits. No decimal point. Those don't count. This has 2 significant figures. Here we have 0.00010. There is a decimal point. The leading zeros are never significant. That's always the case. The zero after a number with a decimal point is significant. So this also has two significant figures. And here we have 0.000106. Leading zeros are never significant. The zero between other numbers is significant. So that's three significant figures. Here we have 2050. No decimal point. But the first zero is between other numbers, so it is significant. The last zero is a trailing zero. There's no decimal point, so it's not significant. So that is not significant, but the first three are significant. So this has three significant figures. And here we have something in scientific notation, 6.02 times 10 to the 23rd. That's Avogadro's number, the number of particles in a mole. And you could write it out like this with the trailing zeros. So no decimal point. These are not significant. That has three significant figures. But if something is written in scientific notation like this, all of them will always be significant. So all the numbers shown in scientific notation are significant, but the powers of 10 aren't part of that. They don't count. They just tell you where the decimal point goes. So here, we want to rewrite these in scientific notation using the right number of significant figures. So 0.0257, we're rewriting this in scientific notation. We need to move two places to the right. So that's going to be times 10 to the minus 2. This has three significant figures. So it'll be 2.57 times 10 to the minus 2. 125.6, we'd have to move two places to the left. So that'll be positive 2. So we have, and it has four significant figures, so it's 1.256 times 10 to the positive 2. Here we have 93 million. This has two significant figures, and we have to move the decimal place 7 places to the left. So this will be written as 9.3 times 10 to the 7th. Here we have negative 65,800.0. This has 1, 2, 3, 4, 5, 6 significant figures. And we have to move the decimal place 4 places to the left. So this will be written as negative 6.58. All those zeros have to be kept because they're significant. Times 10 to the 4. And then lastly, we have 0.000000278. We have to move the decimal point 6 places to the right. So we'll have, and this has 3 significant figures, so it's 2.78 times 10 to the minus 6. Any questions? Yes. This negative? Yeah. There's a decimal point here, so trailing zeros count. Okay. And the negative is just kept. So because this has a decimal point, trailing zeros count. So these are significant and you have to keep them. If there wasn't a decimal point, if it was just written like this, then yes, you drop all these. Here, we're going the other way, writing it in decimal notation. 2.57 times 10 to the 2. Well, we're just going to move To get rid of the positive 2, we have to decrease by 2, so we need to move the decimal place 2 places to the right. And we get 257. 1.25 times 10 to the minus 7. We need to move the decimal place 7 places to the left to get back up to 0. So we'll get 0.000000125. 9.3 times 10 to the minus 4. Again, we have to move the decimal place 4 places to the left to get back up to 0. So we have 0.00093. And here we have 6.580000 times 10 to the 4. Here we have to make sure we keep all of the significant figures. So we're going to move the decimal place 4 places to the right to get rid of the 10 to the 4. And we'll get 65,800.00. And then lastly, we have 2.78 times 10 to the minus 1. You'll have to move the decimal place 1 place to the left, and you'll get 0.278. So here, let's go through these. We want to place the following numbers in decreasing order of significant figures, from the most significant figures to the least. So which of these numbers has the most significant figures? You say this one? Anyone else have any? So everyone. So this has 5 significant figures. This down here, notice there is a decimal point, so all these trailing zeros count, has 1, 2, 3, 4, 5, 6, 7, 8 significant figures. So this has the most. Next is this with 1, 2, 3, 4, 5, 6, 7 significant figures. So this has 8 significant figures. Next we have 890,000.0, which has 7. And then we get to the 60,001, which has 5. Which one do you think comes after 60,001? It's the next after 60,001 and significant figure count. For this has 3 significant figures because the 0 doesn't count. Any other thoughts? This one? Yeah. This has 4 significant figures. Because this 0 is in the middle, so it counts, and that's 4, but the trailing zeros don't. So you can see the red numbers are significant, the black numbers are not. Then we get the 4,520, which has 3. And then the last one is 0.0030, which only has 2. So again, quick review of the rules. If there is a decimal point, leading zeros don't count, trailing zeros do count. And zeros between non-zeros are significant. Without a decimal point, trailing zeros don't count. So the thing that makes trailing zeros count is the decimal point. But any number, any zero that is between non-zero digits is significant. Any non-zero digit is significant. So here, 3,400,100. This has no decimal point, so the trailing zeros don't count. So it has 5 significant figures, because the ones in the middle do. So the rules for calculations with addition and subtraction, strictly speaking, the answer needs to contain the fewest number of decimal places after the decimal point of any number used in the calculation. That's the strict rule. I will be okay if you use significant figures instead of decimal places. Usually they end up the same, but that's the rule. For multiplication and division, the calculated answer can only contain the fewest number of significant figures of any number used in the calculation. So here we have 1.455 plus 3.2. That needs to be rounded to 4.7. So this has one decimal place because it's addition and two significant figures. But if you use significant figures, well, this has two significant figures, this has two significant figures, it would have gotten you the same answer. So usually they work out the same. If you just want to remember fewest number of significant figures, that will always be acceptable. But I will work on the decimal place calculations just because I'm not going to penalize you for doing it more correctly. Here we have 1.40 plus 0.21. And strictly speaking, this should be 1.61 with three significant figures, even though 0.21 only has two significant figures. So this technically increased the number of significant figures. And this is something that could happen. So this is why averages can give you more precise information. Because when you add up a bunch of numbers, you can end up with more significant figures than you started. The start of the idea. So this is two decimal places with three significant figures in the answer. So I guess that was relevant in the lab today. If you were picky about significant figures when you subtracted that weighing dish, you would have had to round your answer, but you should be doing it to the right number of decimal places to be strictly correct. And that's the more obvious thing to do. But here, if you have 1.40 times 0.21, that's 2.94, but you need to round it to two significant figures. So that's 0.29. And here, we have 6.023 times 1,000 divided by 1.56 times 10 to the fifth. Well, this comes out to this number, but the 1,000 actually only has one significant figure. So this actually has to be rounded to 0.04. And here we have 6.023 minus 1.001 divided by 23.002. And this, if you just go through the calculation, you get 0.218328841. And the top ends up with four significant figures after the subtraction. So you round to four significant figures, or you could just say, oh, look, there's four significant figures in my inputs. So I'll round to that. So the right answer is four significant figures, 0.2183. So in general, if you're being precise, you do the addition and subtraction first, calculate the correct number of significant figures, and then do the rest. But in general, you can always just do your calculations and choose the least number of significant figures. That will always be safe. So let's talk about how you go about solving problems. The first and most important step is read the problem. And then you want to identify what you know and what you're being asked for. And that'll often let you identify what you're dealing with, what the situation is, so you can identify the principles that you're going to work with. Also, if you make a sketch, this is extremely helpful because it can help you figure out what you're actually looking for or what sort of formula you need to use to do what you're actually looking for. So you want to determine what's wanted. You want to determine what you know, what you're looking for, and the principle you're going to be working with. There you go. You also need to check your units. You need to check if you need to do any conversions on the stuff you're bringing in. Like, let's say the problem is looking for an answer in meters per second, and your input is in kilometers. You're going to need to convert that kilometers to meters. Once you've done that, you can figure out what the appropriate equation is. If you've listed down what you know and what you're looking for, the appropriate equation is going to be the equation that contains what you're looking for and what you know. And nothing else, nothing outside of that. And then you need to do the calculation, doing the math, using the appropriate units, and round off and adjust the number of significant figures. And then you can do a sanity check at the end. Does this answer make sense? Is it like weirdly huge or weirdly little? Is it on the right sort of scale? So here's an example problem. The Earth goes around the sun in a nearly circular orbit with a radius of 93 million miles. So how many miles does Earth travel making one revolution around the sun? So what do we know? Well, we know that we're dealing with a circle. We know the radius is equal to 93 million miles. And we want to figure out how many miles the Earth travels making one revolution around the sun. So if we sketch a picture, we want to figure out how far it is to go around this circle once, what that distance is. Well, that is the circumference of the circle. So what we're looking for is the circumference. So we're dealing with circles. It's a circular orbit. We want to figure out the distance around a circle. That's the circumference. And we know the radius. So we have a circle. We're traveling around the circle once. We know what the radius is. So we need to know, we know the radius. It's given in miles, 93 million miles. Our answer is supposed to be in miles. We don't need to do any unit conversions. Huzzah. Our equation, well, the equation for the circumference of a circle is 2 pi times the radius. And pi is 3.14159 ... 3.14159 is generally good enough as an approximation of pi for pretty much all practical purposes. So circumference is 2 times pi times the radius. So 2 times 3.14159 times 93 million miles. Or we could write it in scientific notation. 2 times 3.14159 times 9.3 times 10 to the 7 miles. That, if we have numbers in scientific notation, if you have some numbers that you're multiplying together with scientific notation, you just multiply the number part. So if I had, so if I multiply 2 times 3.14159 times 9.3, I will get 58.433574, and it's still times 10 to the 7 miles. And we can round this off to 2 significant figures. So that's 58. And we can also adjust. So we have 58 times 10 to the 7. We'd like it to be in scientific notation to be nice and neat. We can move the decimal place one more place to the left and get 5.8 times 10 to the 8th miles. So 5.8 times 10 to the 8th miles is the distance the Earth travels in one revolution around the sun. If I didn't ask you to write the answer in scientific notation, you could also write 58 times 10 to the 7 miles. You have the same number. And the important equation for this chapter is density is mass divided by volume. And you can rewrite that as mass equals density times volume, or volume equals mass over density. And this book uses rho for density because it's the standard. And because I'm not sure if I went over this last week, I'll go over how you multiply and divide numbers in scientific notation. So let's say this is not working. Let's say I get a different marker. So let's say I have 3.3 times 10 to the, I don't know, 7 times 2.0 times 10 to the, give me a number. Okay, 4. So if I want to multiply these together, I will multiply the fronts. And then when I multiply the powers together, that causes their exponents to add. So 3.3 times 2.0, that's going to be 6.6. And then 7 plus 4, that is 11. So this would be 6.6 times 10 to the 11. Now let's say I was divided. Let's say I had 9.0 times 10 to the 13 over 3.0 times 10 to the, I don't know, 6. So again, first we divide the fronts. So 9 divided by 3, that's 3.0. And then for these, when we divide 10 to the 13 by 10 to the 6, when you divide power, things to a power, you subtract the exponents. So this will be 10, 13 minus 6 is 7. So that's how you multiply and divide things in scientific notation. You multiply and divide the number part, and then when you multiply the exponents together, they add, or if you divide, they subtract. Any questions about that? And if you end up with, if you had 5 times 10 to the 3, wait, no. 3, and you have I'll make it 3 times 10 to the 6. No, I'll make it small. So we have 2 divided by 5. That will give us 0.40. And then we have 10 to the 4 minus 10 to the 3. This is going to be 10 to the 1. But we'd like this in scientific notation. So we need to move the decimal place 1 step over. So this actually comes out to 4. If you're doing math on a calculator, your calculator probably is the calculators that we hand out. They have a button that is labeled EE. So if you have a TI calculator, the button that lets you do scientific notation is labeled EE. What you do is you type the front part. So if you were entering this on a TI calculator, 3.3 times 10 to the 7. you do 3.3, you press the EE button and it'll draw a little capital E. And then you just type set. And that'll give you like a number that will work in your calculation. And when you're answering answers on the homework, the way the homework works, if you want to write an answer in scientific notation, if you wanted to write 3.3 times 10 to the 7 in the homework, so on WebAssign, this would be, 3.3 times 10 to the 7. You would enter this as 3.3 lowercase e 7. And there's actually a problem about entering that properly in the getting started with WebAssign homework. But I just wanted to make that clear because people do get confused. And then on a calculator, what the button is might be different depending on the brand of calculator. But we have TI calculators to loan out, and those have a double E that you press to get the E. It means basically times 10 to the power. And I think it just puts a little E in. Again, it varies from calculator to calculator. Any questions? The E stands for exponent. In that case, that is it for today. We're done, and you are free to go for the day. I will see you all next week. We'll start chapter 2. Remember to come to SI on Monday for your quiz.